Hey everyone, and welcome. Today we're diving into something that literally keeps our industries from blowing up: electrical area classification. We're going to peel back the layers on the complex codes that are the only thing standing between a safe workplace and a total disaster. So let me ask you this. What do these three places really have in common? I mean, on the surface, they seem completely different, right? But believe it or not, they all share a hidden and potentially deadly danger. And that danger is an invisible, explosive threat. You see, whether it's flammable gas or superfine combustible dust or even volatile fumes from paint, all it takes is one tiny spark from a piece of electrical equipment and boom, catastrophe. That is exactly why we have these classification systems in the first place. All right, so here's how we're going to break it all down. First, we'll look at the danger itself. Then we'll get into the two major systems, the International Zone System and the North American Class System. We'll put them side by side to see how they match up, and then we'll talk about why any of this really matters. Okay, so before we get lost in all the specific codes and zones, we have to really get our heads around the basic problem. When you boil it all down, every single one of these safety systems is just trying to answer two really basic questions. Question 1. What kind of hazard are we dealing with? Is it a gas? Is it a dust? Or maybe a fiber? And question 2. How often is that dangerous stuff actually floating around in the air? Seriously, every single rule we're about to cover is built on the answers to just those two things. Let's kick things off with the system that most of the world uses, the IEC, which stands for the International Electrotechnical Commission. The IEC's whole approach is laser-focused on that second question we just talked about, the likelihood or probability that a hazard is present, and it organizes everything into what it calls zones. So it all starts with the most dangerous places, Zone 0. This is the highest level of risk you can have. Think about the space right above the liquid inside a sealed fuel tank. In there, an explosive vapor isn't just a possibility, it's a constant reality. It's always there. And when they say for long periods, what does that even mean? Well, they actually put a number on it. More than 1,000 hours a year. Let that sink in. That's the equivalent of over 40 days straight where an explosive atmosphere is just the norm. It really puts that level of risk into perspective, doesn't it? Now, taking one step down the ladder, we get to Zone 1. This is for areas where a hazardous atmosphere is likely to pop up during just normal, day-to-day work. It's not there 24/7 like in Zone 0, but it's definitely an expected part of the job, like around a pump that's regularly moving flammable liquids. And finally, we have Zone 2. This is actually the most common classification you'll run into. In a Zone 2 area, you don't expect to find a hazardous atmosphere at all. It would only show up if something went wrong. A pipe springs a leak or a seal fails. The risk is low, but it's not zero, so you still have to plan for it. And hey, this whole way of thinking isn't just for gases. The same logic applies to combustible dusts. The zone names are a little different, but the idea is identical. The IEC has a classification for when explosive dust is always there, and another for when it would only show up during an accident. Same concept, different material. Okay, time to switch gears. Let's look at how they do things in North America with the NEC, or the National Electrical Code. Now, the NEC comes at the problem from a totally different direction. It starts with our first question. What is the actual stuff we're worried about? The NEC breaks everything down into three big buckets, or classes. Class I is for your flammable gases and liquids, think kerosene. Class 2 is for combustible dusts, like fine powders of coke or sulfur. And Class 3 covers stuff that ignites really easily, like fibers and flings you'd find in a textile mill. Pretty straightforward, right? So only after they've figured out what the hazardous material is, does the NEC then ask our second question, how likely is it to be in the air? And it answers that by splitting each class into two divisions. And this is where you'll start to hear some familiar echoes of that IEC zone system we just talked about. And it's a really clear-cut split. Division 1 is for any area where the hazard might be present during just normal operations. Division 2, on the other hand, is for places where that hazard would only show up under abnormal conditions. If something breaks or there's a spill. So now we've got the IEC zones on one side and the NEC classes and divisions on the other. They use different words and they tackle the problem from different angles. But how do they actually stack up against each other? Let's put them on the same map and see. Okay, now this is where it gets really interesting, because this chart is like our translator. For gases, look at this. The IEC's highest risk zone 0 and its medium risk zone 1, they both get grouped together under the NEC's division 1. And the lowest risk, IEC zone 2, lines up perfectly with the NEC's division 2. So the NEC basically combines the two highest risk levels into one single category. And you'll see this same pattern when it comes to combustible dusts too. The IEC's high-risk and low-risk dust zones map pretty cleanly onto the NEC's Division 1 and Division 2 for dusts. So yeah, they're two different languages, but they're describing a very similar reality. All right, so we've navigated through the zones, the classes, and the divisions. But let's take a step back for a second. Beyond all the jargon and the codes, why does any of this actually matter in the real world? Well, because whether you're using the zone system in Europe or the class system in the States, the goal is exactly the same. It's about taking a hard, honest look at a workspace, understanding the risks, and doing everything you can to prevent a horrible accident and protect people's lives. In the end, it all comes down to this one simple idea. Every single one of these classifications exists for one reason and one reason only: to make absolutely sure that the electrical gear you put in that area is specially built so that it cannot create a spark and cause an ignition. It's about matching the tool to the job, or in this case, the equipment to the hazard. So the next time you're walking through an industrial plant and you see one of those safety signs, I hope you see a little more than just a warning. You'll see the logic, the risk assessment, and the incredible, detailed systems working behind the scenes to keep everyone safe. Thanks for tuning in.